All right, good morning, everybody. Okay, change the slide title a little bit here. So basically what I'm talking about today is indications of an asymmetric Europa Torus. And if I have time, I'll talk about dynamics. That's a backup slide. But the basic thrust of this is getting down to what our upper limits on the column densities really are that we're seeing. So basically what we've done is we have taken a thorough look and reanalyzed the INCA observations of the Jovian system. And just like previous work done by Barry, we use also 55 to the 90 kV channel because it's less scattering in that channel. And what we've done differently here is that we use only image integrations with negligible background. So we're not doing any background subtraction because there's simply no background in there. We keep the attitude fixed, and then the basic methodology is that we use a forward model of neutral gas densities. We assume H2. Of course, we don't know what the species are, but this is what we assume. And we do include then the INCA point spread function within the forward model. So that in itself is a different approach than Barry took. So we're going to check if we get basically the same results. Okay, this portrays the four sort of image exposures that we're starting to look at. And basically this one down here is the one that we're concerned with in this presentation. If I have time, I have backup materials for this one as well. But the thing that made at least me interested was that there's sort of an apparent small relation with the asymmetry or symmetry in the image and the Europa location. So for instance, in this image, it's very apparent that the emissions are off to the right side and the same side as Europa. When Europa moves behind Jupiter, it seems to be more centered on Jupiter. And then this one here is a little bit more uncertain. And this one where Europa is to the left of Jupiter, the emissions seem to be off to the left as well. Of course, statistics is not very great in this, so we had to take great care of actually analyzing these images. I want to make one important remark on the column densities here. If you just take your differential intensities that we observe with INCA, they are about, that's the top of the color bar essentially, it's about 0.6 in differential intensity. If you then take and assume your maximum proton intensities measured by Galileo APD, and if you assume that that is your maximum proton intensity, you can derive a lower limit on your column densities. And that lower limit will be in the range of about 0.5 to about 10 to 12 per square centimeter. And of course, it depends really what cross-section you're using. There are two cross-sections out there in the literature that will give some range to this. So this is an important takeaway point here. This is your lower limit from the INCA observations of the column density. A quick review of what Barry did in his 04 JGR paper and the work before that as well. Basically, he used a 15-hour INCA integration time. And from that, they deconvolved the image from the point spread function. And basically what then happened was that they compared the deconvolved image shown here with a simulated image built up from a forward model. They obtained a range of spatial distributions. The radial full width of half maximum is from 2 to about 5 RJ, and the vertical is about 1 to 2 RJ or something like that. They did assume the cross-section by Rudd, which is slightly higher than the one we're using. If you assume H2, they arrived at this column density. And note that I'm not talking about absolute densities here because that is dependent on your exact spatial model. So they arrived at about 10 to 12 per square centimeter. And also total neutral gas content of about 10 to 34. It's less, and that was assuming for H atoms. It's less if you assume H2. It's about half, I think. And basically, they had to assume a symmetric torus and also Jupiter-centered emissions to fit the images. So in this work, the methodology is almost the same, but with one big difference. We include the INCA point spread function already in the forward model. So we do the point spread convolution on the ENA image, and we compute the ENA counts from that. So we simulate an ENA counts image and compare it directly to the untouched count image observed by INCA. And then, of course, what you do in standard statistical approaches, you compute your reduced chi-square and for between the simulated and the observed images, and then you tweak your neutral gas models that I'll talk about in a moment. And we assume that the ion intensity is fixed, and you do that until you reach statistically acceptable reduced chi-square solutions, and then you analyze those solutions. So that probably is a 2-hour talk already there. Other assumptions, we did an approximation of a magnetodisk. We use a dipole field, but that's okay because if you have a magnetodisk, the solution is pretty insensitive if it's a dipole field or not. Isotropic pitch angle, similarly, since most of the neutral gas is confined to the equator, the pitch angle distribution is the fits are pretty insensitive to the pitch angle distribution. Ion intensities, these are the Galileo EPD radial profiles at 70 keV, which is the geometric mean in the channel, and simply model fit here. Very important here is that at your inside of Europa's orbit, the ion intensities drop to the bottom. There is almost no energetic ions, at least for this, inside of the orbit of Europa. That is very important, because we cannot say anything about neutral densities from the INCA images inside of Europa's orbit. So keep that in mind. Neutral gas, basically what we did, and we assumed also H2. We took a parametrized Gaussian distribution centered on Europa. Free parameters here are absolute density, azimuthal, and radial widths. Then we also took a parameterized sort of 1R² model of a more symmetric H2 cloud. The free parameters here are absolute density, the radial slope, and the vertical thickness. Please note that a lot of these free parameters, you can sort of fix them at beyond some point, because the fits are less sensitive to the neutral densities beyond certain radial and vertical widths. And this is largely due to magnetodisk confinement as well. We did have a third component in there, basically reproducing the low-altitude ENA emissions, the Jupiter-centric emissions. And we turned out to actually put the free parameter at basically the ENA intensity itself, just to be able to scale this up and down. It's much, much less than a pixel, but it can be very strong. Just quickly, this is the cross-section we used, and this is from the Oak Ridge Red Books. There is another cross-section out there by Rudd et al. in 1983 that is higher than this, and that will result in lower required column densities. Okay, let's go into the results very quickly here. This is the one observation that I circled in red before that showed you an apparent asymmetric emission pattern from the Jovian system. So Jupiter is obviously in the middle here. Europa is off to the left side, and there seems to be sort of an excess of maybe twice as much counts on this side than on this side. And the question is this really real? Down below here is the best reduced chi-square that we found, including the point spread function, of course. And in the next image, I will then show you what this one looks like without the point spread function. So this is what you would see if you had an ideal imager. And basically, you can see the components here that we use in the simulation, and this is obviously also for the best fit that we found. So let's start with this stuff here. In the middle is the low altitude ENA emissions. Europa sits over here. The excess on this side here is the A is missing here. Asymmetric H2 cloud centered on Europa on the left side, plus the contribution also for the more symmetric H2 cloud component. And over on this side, you basically only see that remnant of the symmetric H2 cloud. Okay. All right. So here is the symmetric H2 cloud that we needed to obtain the best reduced chi-square. Because it's worth noting, if we only use the Jupiter-centric emissions, it makes the ENA image too peaked around Jupiter, and it is very clear. And the max column density here is about 7 times 10 to the 12 per square centimeter. A couple of points that we need to re-emphasize here is that within this region here, we can't say anything because there's no energetic ion intensities, remember. And then also outside about 15 RJ or so, the energetic ion intensities do go down, so the fits are very insensitive to what is going out here in terms of neutral densities. So it's really these boxes that we need to look at and that their fits are sensitive to. So this is the asymmetric H cloud that we put centered on Europa. And important, this is only marginally better fit than only a symmetric H2 cloud. So we need to study this further. So I want to re-emphasize it's only marginally better. Let's go on, since I'm running sort of out of time here slowly. Takeaway point here, which I think is important for the coming discussions. When comparing ENA and UV observations and model results, it is my opinion that one should compare column densities and not absolute densities, because absolute densities, they're dependent on the assumed spatial morphology and spatial morphology model. Our results show that the INCA images are indeed consistent with column densities between about 2 to 7 times 10 to the 12 per square centimeter. We assume H2. So I said that this reanalysis, we took a different approach than what Barry did, and still we arrive at the same range as they did. This range, of course, it depends heavily on what the cross-section we assume. So if we assume the same cross-section as Barry, we basically agree right on the dot. Ion intensities, we do fix them, of course, but they are likely dynamic, and I think a lot of you have seen evidence for that. We do see it in the shorter time scale integrations as well. I have that as a backup slide, but on a 10-hour average time scale, the ENA intensities, they are fairly constant, to at least within a factor of 2 to 3. So let me end with these 2 points down here. If there is an asymmetry persistent in the rest of the INCA images that we can show, then that, of course, is our support of a neutral gas cloud originating from Europa, since it's then would be centered on Europa. However, when it comes to origin of the symmetric cloud, we can't tell from the INCA analysis, of course. And so this is still a very open question that we need to discuss. So with this, I'd like to take questions, and I look forward to the next presentation on this subject.
Questions for Pontus? Fran, can you come up to the mic, please?
This is a very nice presentation.
Thank you.
Very interesting. I'm talked a little bit with Barry. I'm wondering if you've begun to consider charge exchange with singly ionized species, and I'm wondering, whether you've thought about whether this is a significant amount. If you've got a fairly high density of O+, S+, those sort of things, can you give us an estimate of how they would compare with charge exchange with H2?
Yes, they are significant. If you look at the theoretical cross-section between protons and O+, it is about a third of what it is for H+ and H2, which means it could be actually a contender to it. So it comes down to what are really the O+ densities out there, and that's something we really need to look into. So it could be significant. We just don't know yet. But we have considered it and discussed it, and it's actually a very interesting implication to it.
Good, let's talk more.
Analysis. Yep. Yes, at Europa's orbit, correct.